If you've been following this channel, you know that recently we began a series of videos on developing a high-powered, computer-controlled, directed energy device. And as I promised, we're going to be continually increasing the power and the capabilities of this system, as you can see. The results are impressive. Actually, they're very exciting. So much so that Alex and I have planned a trip to an arms dealer convention. We're going to get some really expensive suits, maybe a gold earring. But seriously, to keep things interesting, today we're going to deviate from that topic, and I'm going to cover a different type of device that can be used for increasing the fuel efficiency and the thrust of jet engines without using a drop of additional fuel. Now, we have done a lot of videos on propulsion. Early on, we've done a series on building and designing your own large rotors or propellers for drones or other types of vehicles. We've also done a series of videos on rocket motors, how they work and how to build both solid rockets and hybrid rockets. And then we tested them. That was a lot of fun. We've also done a series of videos on turbojet engines. Again, the principles, the engineering, how to build one yourself at home, as well as testing them along with an afterburner. This is a pulse jet engine. This is a pulse detonation engine. It's very closely related to rotating detonation engines that have become kind of a topic of the day with all of the developments that have been going on with NASA. And this is a commercial turbojet engine. These are augmenters. Now, if you think I misspoke and meant to say afterburners, I didn't. This is a completely different animal, and it operates by completely different principles, and we're going to dig into that. Now, I didn't invent these. These things have been around for decades, and there's a lot of literature out there to support the fact that these things can substantially improve the performance of these types of engines. But there's very little research out there to demonstrate how they would work with continuous output jet engines. The few papers I found suggest that they don't work. And I found that very strange, because if this principle of operation works on the microsecond scale and the millisecond scale, why shouldn't it work on the second or indefinite scale of a continuous output jet engine? Now, it's possible, because of the lack of data out there, that the few papers I read were wrong. And so we've got a jet engine, we've got augmenters. We're going to go ahead and we're going to test that today. Now, if you're interested in jet engines and you want a lot of information, take a look at our original series. But briefly, what we have here is a commercial RC turbojet engine. This is the swiwin 300B single-stage RC turbojet. The B stands for the brushless starter motor in the front, and the 300 stands for 300 newtons of static thrust at sea level, which is about 66 pounds. So this is a pretty beefy RC turbojet engine. Now, we purchased this engine from a local distributor here in the US called Bad Boys, B-O-Y-Z RC. And they don't sponsor this channel. We don't have any sponsors. But even though it's a small company, I've been very impressed with their pre- and post-sales support. I've called them at all hours, and they're always very responsive and very helpful. And it's very nice to have a company that can tune, maintain, repair these engines in the United States, as opposed to having to ship everything back to China if you have a problem with the engine. So if you're in the market for an engine like this, I would definitely put them on the list of companies that you should give a call. Now, the way the engine operates is that in the front of the engine is a single-stage centrifugal compressor that draws air into the engine and compresses it to 2 to 3 atmospheres in the combustion chamber. That's where fuel is injected and it is ignited, and once it burns, it releases a lot of heat and substantially increases the volume of that pressurized gas, which then rockets out the back of the engine to produce thrust. This is a reactive engine. a momentum-based engine. The acceleration of the gas out the back is what produces the force in the opposite direction, Isaac Newton. Mass times velocity. If you want more thrust, you either need more mass and/or more velocity. Now, the compressor requires energy to drive it, a surprising amount of energy. In this engine, at full throttle, that single compressor wheel uses over 100 horsepower to turn it. In this little engine, it's pretty impressive. And where that power comes from is in the exhaust of the high pressure, high velocity exhaust is a turbine. The gases impinge on the turbine and cause it to rotate, and that rotation is transferred to the compressor wheel in the front. But by extracting that much energy from the gases cool and they shrink. So the velocity of the gas coming out of the back end is lower than it would be if you didn't have the compressor or the turbine, but you have to run the compressor, so you're stuck with that. Now, the way an afterburner works is that all jet engines pass a lot more air through them than they need to supply the oxygen to burn the fuel. It's not a stoichiometric mix of just enough oxygen, just enough fuel that everything gets consumed. So what comes out the back of the engine is hot, but it still has a lot of oxygen in it. So the afterburner injects fuel after the turbine so we don't melt it, and ignites it, reheating the gases, expanding them again. And so in order to get out of the nozzle, the only way to do that is to go faster, so we get more thrust. Now, these things are remarkable little devices because they can have few or no moving parts. They're lightweight, and they can increase the base thrust of the engine by 50 to 70%. The downside is they're very inefficient. They use a lot more fuel than the underlying engine. And the reason for that is that the efficiency with which any internal combustion engine can convert chemical or heat energy into useful work, in this case, high velocity exhaust coming out of the back, is directly related to the compression ratio of the air and the fuel at the point that you combust them or you burn them. That's why diesel engines are so efficient compared to, say, gasoline engines, because they have a very high compression ratio. Now, commercial turbojet engines with their multiple compressor stages can actually reach compression ratios that are higher than a diesel engine. They're very efficient. Single-stage RC turbojets, not so much. The problem is the afterburner is operating after the turbine at even lower pressure ratios than in the combustion chamber. That's what makes them very inefficient. So if you take a look at a video on YouTube where they take a turbojet and they fire up the afterburner, you'll see what looks like a blowtorch coming out of the back. It looks really cool, but that hot incandescent gas represents wasted thermal energy because it's not heat that drives the engine forward, it's pressure. Nevertheless, if you want to take off from a carrier deck or you're in a combat maneuver, they can be very useful devices. Now, specific to this engine, we have an electrical feed line and we have a fuel line. The fuel line and the electric line go forward here. This fuel line has a little shutoff valve here and runs to this fuel pump over here, which draws its fuel from these two 1-liter tanks. Each of them contains Jet A with 3% turbine oil added to the fuel to lubricate the bearings. This pump receives its signal and its power from this junction box here, which is in turn powered by a 12-volt or 3S battery. The control over this is, or I should say actually the feed from the engine also goes into this box. So this thing can send power to the starter motor, to the glow plugs, and receive signals from the thermocouple that measures the exhaust gas temperature as well as the RPM of the engine. This in turn is then hooked up to the GSU, or the ground support unit. It's a little computer with pre-written algorithms for automatic startup sequence, shutdown sequence, and limits for overtemp or for overspeed. And it allows you to control the unit with a simple menu control and a few buttons, so it's pretty convenient. On the bench, we then have this thing controlling through this box to here a pulse width modulation source. This is basically a servo controller that changes the frequency of the pulses, and that's how we can throttle the engine up and down when we're doing the testing on the bench. Now, because we're going to be testing this engine as well as these engines, multiple engines, we decided to build a dedicated support stand for doing this. We have a very heavy optical table here that weighs about 450 pounds, about 200 kilograms. And bolted securely to this is a wooden frame, and on this frame are two linear bearings that support these brackets here and have a very high load capacity, but almost no rolling resistance. So mounted onto these bearings is a heavy-duty beam that sticks out of the front onto which we can mount our motors. This beam then is limited in its forward motion by hitting this plate. This is a blast plate. Because we are going to be in relatively close proximity to some pretty energetic events, in case things go really sideways, this helps to protect us because we're so close. What prevents this thing from moving backwards under thrust is this load cell here, which is attached to this load meter that can read up to 1,000 newtons or about 200 pounds of forward thrust. And that is how we're going to be testing the motor. So, enough talking. Let's get this thing outside and let's make some noise.
Ready?
Mm-hmm. What do we do with this?
Yeah, keep it. Yeah.
All right. Remember to go slow to the bump.
Yep.
And straight out until the second set of wheels pass the bump. Keep going. Keep going. A little forward. About there.
Good?
Yep. That looks good. Okay. So I can start my process now.
Okay.
All right. Yeah, that's not rolling.
All right. It's quite windy though.
Yeah.
What can I do?
Bring the cord out.
Okay, good. Nice.
So while he's finishing up the fine setup here, just wanted to give you a little bit of a reminder. You might have noticed on our channel, we don't have any paid sponsors. We've debated it, but we find that it tends to interfere with the flow of the videos, and it can be a little bit annoying, especially when you're putting up with advertisements on top of that. So the only support we get is from YouTube and Patreon. And so by subscribing to the channel and by commenting, you help to push the algorithm, causing YouTube to distribute our videos to a much broader audience. And that will help us to grow and help us to afford to spend the time and the money that obviously we're investing in this project. Thanks. Now back to the video. So I've turned on the fuel line here so we can deliver fuel to the system. And a couple of things that you're going to want to watch. This force gauge here will read the thrust of the engine as we're ramping this thing up. You'll also notice on this GSU. The top two lines. The top line shows the RPM of the engine, which tops out at about 98,000 RPM. And the second number is the EGT, or the exhaust gas temperature, which would be a little bit below 700 degrees Celsius. And beyond that, you can see that there's a current meter that measures the amount of current flowing to the engine, which originally is going to be very high when it's starting the spin up, and also when it's firing up or heating up the two glow plugs inside of the engine. The initial sequence, because this is going to get very loud, will sound relatively quiet as the engine is beginning to spool up. And then when it reaches a certain RPM, around 4,000 or 5,000, it will open the first of the low flow solenoids inside of the engine and spray a little bit of fuel at the glow plugs to get everything ignited. Once it reads that we're getting some burn and some increase in temperature, then it will automatically ramp up the speed to 33,000 RPM, which is the idle speed of the engine. And then once that stabilizes over about 4 or 5 seconds, then we can go ahead and ramp up to full speed. You'll notice those things, but also in the background, keep an eye on the fuel container. This thing is really thirsty, and it's impressive how fast it drinks the fuel. So you ready?
Yeah, I'm ready.
Okay.
I say that. I'm not really ready.
Oh, something else that I should have mentioned. I added some lead bricks to bring the total weight here to about 800 pounds, and on the wood boards, which elevate the table off of the driveway here, we get a lot of friction, so there is no way this thing is going to move.
Yeah.
In addition, we have a fire extinguisher here, and I have this electric blower set up. If everything goes fine, we're not going to use those things. But in the off chance that the engine sort of shuts down suddenly for some inexplicable reason, it can flood with fuel, and you don't want to have jet fuel sitting inside of a hot engine for a long time, because it can coke and it can damage the injectors. It can also damage the solenoid. So if we need to, we can use that blower to cool the engine down rapidly before we clean it out. So hopefully we don't need them. All right.
So here we go. Ready?
Yeah, that's looking better. All the way up.
Ignition,
Now go
sit
down.
down.
Almost all the way, but not quite. That's good.
I'm at 12%.
Yeah, that's good. I think it's doing the ignition.
I don't think it is.
Put it down a little lower then.
8%.
There.
Have to go to 0.
Yeah,
You have to go
okay.
to 0. It's not.
All right.
Yeah. There we go. I hear the firing.
Started.
Yeah. Preheat.
Yep.
Okay. And if you guys can see that.
I love that sound, and I love that smell.
Preheat. Got it.
Now it should go all the way up on its own to 33,000.
Yeah, and if you can see down here, guys, you can see the levels. Yeah. Oh.
Wait, leave it. It's stabilizing. Let it do it.
Okay. Yeah, it says fuel ramp there.
Yeah.
And if you guys can see, it says running on there, and you can see the RPM, temp, pump, and RC levels on the bottom there.
All right.
Okay, now it's in the cooling mode, which is what it does as soon as after you kill everything because it's too hot. So now what it's doing is it has its, you can hear it now.
It'll continue to cool off until it gets to about 70 degrees Celsius, and then it turns everything off. And that's all automated inside of the GSU. Notice we used 1 full liter of gas plus about half another liter. So this thing is thirsty. That smell, though, is phenomenal. It's an interesting statement. They say jet engines don't burn kerosene, they burn money. Even a small engine like this uses a lot of fuel. And it's an interesting thing about these engines because they cost a few $1,000s, and they have a 25-hour interval before you have to send them in to get them maintained, have the bearings checked, the injectors checked, the solenoids and filters checked. And that'll cost a few $100s. So you can imagine that it costs about $10 an hour to run this engine. But the big number is this. Consuming about 1 liter a minute, this engine will burn about 60 liters per hour, or about 15 gallons, or at about $4 a gallon, about $60 per hour. So in that 25-hour period, you will spend $1,500 on fuel. Pretty impressive. So now what we're going to do, we got this up to 282 newtons, pretty close to the spec because we're at about 1,000 feet. So you figure about 290 at sea level, within a few percent of the spec rating. So that's not bad. So now we're going to take a break, and I'm going to install the Augmenter, and we're going to see how that compares. So everything is installed and tightly bolted down. And to explain basically how does an augmenter work, you have to understand how it's designed. If you look at the front edge of the augmenter, it has a large radius of curvature. It's sort of like a donut or a torus. This was formed by taking 4 right angle segments for automotive exhaust fittings, welding them together into a ring. And then on the outside diameter, there's a thin sheet metal cylinder that's formed that matches the outside of the torus. And then there is a second cylinder inside that's tapered. It starts at the inner diameter of the torus and flares outward until it eventually reaches the straight cylinder back here, where it's welded up as a knife edge. It's kind of interesting because if you were to take a knife and slice through this and look at it sideways, it looks remarkably like an airplane wing. Like you took a wing from an airplane, cut it off at the root near the fuselage, and literally bent it into a cylinder. And the way it operates is based on the fact that whenever you have a high-speed stream of gas moving through a stagnant atmosphere, the pressure inside of the stream is lower than the surrounding pressure due to the conservation of momentum. Now, if you're kind of curious about that, why that does what it does, is consider a blowtorch. When you fire up a blowtorch, you're producing a lot of hot gas, but what comes out if you can see this, is a very collimated beam, almost like a cylinder. It doesn't spread wildly into the air, even though it's hot and it's moving very fast. And because of the low pressure, air is entrained from the surrounding atmosphere into the stream. So even at a relatively small distance from the burning torch, I can put my hand in front of it because of all of the additional cold air that is sucked into the stream. Now, if you want even more background and to understand the fact that the air is being entrained, take a look at our previous video called Controlling Chaos, where we built the big tornado chamber. There I actually demonstrate ambient air being sucked into this high-speed stream of air. The reason it matters is because the air or the exhaust coming out of the jet engine is moving fast, really fast, around 500 meters per second. If it was at room temperature, it would actually be supersonic. But because the speed of sound increases with the temperature, in that hot stream, it's actually not supersonic, but it's clipping along. And as a result, the air pressure inside of that stream is very low, and it's entraining a huge amount of air into and across the leading edge of the augmenter. The air is moving, and because it's moving, the pressure in front of this leading edge is lower than ambient pressure. The same thing is happening at the rear end, but because of all of the entrained air and the slowing of the velocity, as well as the much larger diameter, the differential pressure between the stream and the air outside is lower. In addition, it's acting over a negligible surface area. The result is that the tube experiences a differential force against its two ends. It literally wants to be sucked onto the engine, but we don't let that happen. So in theory, this force will be added to the thrust of the engine and should increase the amount of force or power that we make with the engine. So we're going to find out. Let's make some more noise. That sounds good. What do I do with my headphones?
Yeah, so you don't blow your ears out.
Yeah, okay.
All right. So, my turn now? All right.
Turn.
Here we go. Okay, so all right, all the way up. Ready. And then down. Ignition.
Don't you have to go all the way to 0, like you said last time?
No. It's doing it now, so.
Okay.
Preheat. It's getting there. It's doing it. You can see down here.
Yeah.
Is that okay?
Yeah.
Okay.
Yeah. Okay.
Because I'm just doing what I'm seeing here, but
Right.
I don't know if I was doing a good job. So
We're doing in the cooling mode. We've
Yeah.
still used about 1 liter of fuel.
yeah.
So what's interesting, as you noticed, is that we actually lost a little bit of thrust with this setup here. I don't understand that. Do you want to do this run up once more? We've got enough fuel. Just to prove again that we got the same number. I think we should, because it is set up and it'd be trivial to do it.
Yeah, okay. So guys, we're gonna be doing this again. So we just ran it, and so we're gonna run it again just to prove that the values that we just showed you on this little
Are
GoPro.
consistent.
Yeah, that we're not faking it.
Yeah, right.
Exactly.
We're not faking it.
Not faking it.
Okay.
Yeah, exactly. Okay, so headphones on again. Mics are on.
Yep.
Everything's good. I got my headphone. All right.
Try it again.
How do I reset
See the
this,
0
though?
in the middle?
Yeah. Okay. Let me make sure this is good. And it keeps doing its cooling thing.
Yeah.
But 0, this thing.
Yeah.
Right. This thing.
Yeah.
Hold
Push
it.
it. There.
Or just once.
And then it's working.
Okay. Good. All right. Okay. We'll try it once more now, just to prove to you guys. All right. All right. Here we go. Hopefully it's not gonna not work. Let's go. Ignition stick down. Can't go all the way to 0. It doesn't seem to work if I do that. Oh.
Oh, that time it worked. Okay, leave it. Let it ignite. It might be slightly different when it's already kind of warm.
True. Yeah,
You know.
could be. Yep. And I hear the
Yeah.
Yeah.
And notice the current. You see the current there? 7.8 amps.
Right.
That's because it's running both the blower, the motor, as well as the glow plugs. And then that will actually go down to about 1 amp or less than 1 amp when it's just operating the computer. But as long as that's running, it's still using the starter motor and it's still using the glow plugs. Fuel ramp.
Yeah.
It's definitely going up.
Yeah, there we go. I never liked this.
I know, it's exciting. Just wait till we get to the pulse detonation engine.
I won't be here for that.
Oh, yes, you will. Oh,
Yeah,
yes, you will.
Yeah, I'll be here for that.
Yeah, see the current? Now,
Yeah. Right. I mean, you see.
now you better ramp it up pretty quick before we run out of fuel.
I will.
Can't wait.
I don't like.
Okay.
Okay. Just a second test. I thought that was good.
All right, so we're going to get this thing inside and I'm going to explain to you what's going on. So I was kind of disappointed with the result. As you could see, we actually lost about 10 or 15 newtons of thrust from the basic engine. And I didn't understand why that would be, because if these things in fact work for microseconds or for milliseconds, why shouldn't they operate on a continuous output engine like this for seconds or indefinitely? So I did a little bit more research and I contacted the author of the article on which I based the design of the Augmenter. and explained to him what was going on and asked him if he understood what might be happening here. And he said, you got the first part of it right, but he said there's another principle operating that you haven't accounted for. In a continuous flow engine, we have a tremendous flow of exhaust coming from the jet, as well as all the entrained air that's being drawn in with that jet blast, producing a relatively high velocity of gas moving steadily through the tube, dragging along the inner walls of the tube, producing a force that's opposite the force that's produced by the differential against the front and the back of the augmenter, effectively wiping out the advantage of using the device. In an intermittent type of thrust engine like these, before a pulse of gas comes out of the engine, the air outside as well as inside the augmenter is not moving, it's stagnant. And when that blast of air comes into the engine at the access of the tube, there isn't enough time for all of the air inside of the engine to be entrained into a generalized flow in the same direction as the exhaust. And so what you create is called a vortex or a torus. It's a turbulent flow that's a lot like a smoke ring, where the center portion is moving very quickly back out the end of the tube. But the outer portions of that smoke ring are actually moving in the opposite direction along the walls of the tube. And so if there is any frictional drag, it's actually working in the same direction that we want the augmenter to act in order to add to the thrust of the engine. That makes some sense. So I thanked him, and what we're going to do in our next video is we're going to attach this augmenter to the pulse jets, and we're going to see if in fact it works. Now, if you like what we're doing on this channel, please consider subscribing. Really appreciate it. We're getting tantalizingly close to 1 million subscribers, and the bigger we get, the more we can afford to bring you. So I want to thank you very much for watching. Stay safe, have fun, and I'll see you soon.